we're going to switch from using Riemann sums to using definite integrals. Okay, these are actually a replacement for a Riemann sum. And the definite integrals work when you have boundaries. Okay, just like when we're finding the area under a curve, we're finding it from a point to a point. When you have that situation, or when you're integrating from a start point to an end point, that's a definite integral. If you don't have those boundaries, that's an indefinite integral, and that's the same as an antiderivative. But definite integrals, you're not going to have your constant of integration, that big C that we add on to the end. You're just going to have a value. So this is the Riemann sum. This is being replaced with this notation for our definite integral. Okay, A and B are the range that you'd be finding the area from. Now this dx here, that comes from our antiderivative definition. Okay, so if I say that dy over dx, that's the same as f prime of x. Well, to think about it, this isn't actually what's happening, but to kind of see where this notation comes from, if I'm going to differentiate or integrate this to find out what y is, if I want to have y equals f of x, well, the derivative of y would be dy. Okay, so if I'm going this way, differentiating, if I take the derivative of this, it brings me to here. But really, I just want y to be on the left side, so I'm going to move this over here. Okay, and that's how we get this dx over here, because I want dy to be f prime of x dx. That way when I integrate, this turns into y, and this, which is kind of like the chain rule, because the derivative of my function is my f prime, and then chain rule, the derivative of x is dx. So I want all that to be on this side, and I want just the dy to be on this side. So that's why you always need to have a dx. And this is going to play a bigger part when we get into integration by substitution, which is a little bit more advanced integration technique. It's important that your d here is the d of whatever's inside your function. So it'll be kind of like our chain rule when we get to that. Okay, but I just wanted to let you know where the dx comes from. It is important. You have to have the dx, else you can't integrate. All right. To evaluate these things, okay, all you're going to do is you're going to take the antiderivative of your function and take, so big F is the antiderivative. So that means the derivative with respect to x of the big F equals little f. So I'm going to take the antiderivative of this, and I'm going to plug b into it, and then I'm going to plug a into it, and I'm going to subtract them. So an example, okay, if I want to find the area under this curve from 3 to 5, okay, that means I'm integrating from 3 to 5 this function over your dx. Okay, I can break this up and give it to each individual piece. So I've got x squared dx plus, I take the constant up front here, 5 integral of x dx, and then minus 1, minus the integral of 1 dx. Okay, and all these are from 3 to 5. Well, if I integrate this, or, yeah, I'm going to raise the power by 1 and drop the reciprocal. Okay, same thing here, raise the power by 1, drop the reciprocal. So I've got 5, and then the reciprocal of this is 1/2. So those are times together. Here, this turns into just x. And I want to evaluate this from 3 to 5. So you'll see this notation also. Okay, that means I'm going to plug the 5 in first. So 5 to the third is 125, so I've got 125 thirds. 5 squared is 25, times 5 is 125 halves, minus 5. Okay, I've got that. That's my function at 5. I need to subtract my function at 3. And that's going to be 27 thirds plus 45 halves minus 3. So I'm just going to bring the calculator up real quick so we can do this. So I'm going to do 125 thirds plus 125 halves minus 5, and I'm subtracting 27 thirds plus 45 halves minus 3. 212 thirds. So it's important that you do all this work. I'm going to show you a way to check it on your calculator also, just so you guys have a way of checking your answers. Your calculator is set up to do definite integrals. Okay, most of your calculators won't do indefinite integrals, but they'll do definite integrals. And so what you want to do is math. Here, function integrator. Okay, that's what this is, function integrator. I want to integrate this function. So you input your function, x squared plus 5x minus 1. You have to tell it the variable you're integrating with respect to. So we're integrating with respect to x. You tell it your lower bound, which is 3, and then you tell your upper bound. And all those things are separated by commas. Close your parentheses, and then you hit enter. And we get the same answer that we had when we did it the other way. Okay, so you can't check your answers on your calculator. Don't use it as a crutch. Make sure you get the process and show your work. I've got some rules that go along with definite integration. If we're integrating from, if our lower bound and upper bound are the same, we're going to have 0. And the reason that is I'm trying to find the area of that rectangle. The rectangle is a line. Okay, because here's A. Okay, let's say that's A. There is no area under there because I have no width. My width is none. I'm going from A to A, 0 width. So I have 0 area. If you have a region, you can split it up into smaller regions if it's more convenient. And I'll show you one example where you have to do it this way, but let me put in where A, B, and C would be. So if this is A and B, this would be C. And the area from A to B is the same as if I just found the area from A to C and added it to the area from C to B. So basically we're splitting these up into 2 different integrals. And that's allowed. If you have a constant, you can pull that up front. That's something we've talked about before. If you're adding or subtracting 2 functions, you can give them each their own integral. We've talked about that before also. Another one up here that I forgot to put up. If you're integrating from A to B, f of x dx, that's going to be the negative of integrating from B to A of f of x dx. Okay, so if you switch the order, you're going to get a negative of what you would have gotten. Okay, absolute value. Absolute value requires you to take advantage of integrating from A to B using 2 different subintervals. Okay, so if you think about an absolute value function, let's just say the absolute value of x. And if I were to integrate this from -2 to 2, well, I'd really be integrating under a curve. Here, I'll change my picture to match ours. Okay, that's the absolute value of x. If I want to integrate from -2 to 2, well, for this area here, this line is actually the line y equals -x. Okay, and this would be the line y equals x. So for this area here, I'm going to be integrating from -2 to 0 of the opposite of my function, so of -x. I'm going to want to add that to the area that I get for this region, which would be integral from 0 to 2 of this function. Okay, so that's why when you have an absolute value function, you're going to switch the sign. So you're going to make the negative of that function and integrate it from a, so from your left bound up to your 0. Okay, c is the 0 of the function. So let's say f of x was 2x plus 8. Okay, if I solve this, I get a 0 for the function at -4. Okay, so I would go from a to -4 on the function -2x plus 8, and I would go from -4 to b on the function 2x plus 8. And then I would add these two definite integral answers together. Okay, depending on what a and b are. I mean, if a is 2, I wouldn't need this function at all because I would be in the area that is all underneath this positive function. Okay, but that's how you deal with absolute values. So there's always a trick to absolute values. If you remember when we were taking the derivative of them, we changed them to, square roots squared. Okay, well, this is the trick for doing integrals of them. Okay, so that covers all the properties and the basics of definite integrals. The next one will be about a couple special things you can do with definite integrals.